Is it time? Okay. So, first of all, thanks all of you for the time you spent in the afternoon discussing your projects. I think the largest fraction of you are already in good track to formulate a project and write an abstract by the end of the week. For those of you that weren't around or couldn't make it or whatever, if you have not discussed your project with either me or Jeff, then please come and talk to us sometime during the day today so that we can guide you a little bit on what makes sense and what doesn't make sense. Okay? So up until now, and I'm very tempted to switch on the lights for the board because is it Lumière 2? No, it's not Lumière 2. I want Lumière 1? Great. Okay. So what you did with Antonio was work out for various sorts of excitation. So if your wave function looked like a sum of internal states of a projectile times the relative motion between this projectile and the target, if your wave function looked like something like that, you worked out the Schrödinger equation for the partial wave coupled equations that you'd get if you replace this in the Schrödinger equation and then project it on specific channels. So you'd get something that was the kinetic energy operator, some diagonal coupling dependent on R, an energy that might depend on the channel because now you've got something that might bring in excitation, and you'd get couplings to other states. Right? And so whether these states were just excited bound states or whether they were excited into the continuum and therefore you then discretized the continuum and created bins, you'd still have a similar coupled channel equation for your problem, and you'd match asymptotically your wave function asymptotically would go as some Hankel function incoming, S matrix, and now, I don't know, IJ, Hankel function outgoing, right? So you'd have such a condition, and you'd solve these, and what you've been doing in your homework, both yesterday and the day before, is solving this equation in a particular number of ways. The physics then is contained in how you define these couplings that are a function of R in this context, okay? So I'm just reminding you, because today I want to talk about something a little different. Now I want to consider cases in which you have different mass partitions. If you have different mass partitions, what I mean by this is that if you start out with a target of mass A, you'll end up with a target that doesn't have mass A, either has more or less mass. So it means there's parts, nucleons, that are being transferred onto the target or out of the target. Or even fusion. We'll discuss fusion. So in the end, you end up with a different mass partition. So up until now, as I say, you've only considered different sorts of excitations, either to bound states or to either to bound states or to the continuum. You've also considered rotational effects, so excitations of targets in that context, but you haven't really considered this transfer of mass. So let's look a little bit at a simple case and see how that equation changes in those circumstances. So I want you to think about the deuteron case as the prime example. And we will be moving back and forth between this particular example that's nice to illustrate the problem and the general case where you have any odd 3 particles and one part of it gets transferred. So you start out with this deuteron channel, and I better get this. Did already? Yes. So you start out with this deuteron channel, and by deuteron channel I mean that you've got a relative motion between a bound state of the deuteron and the target A. And so you define your coordinates, big R being the relative motion between the deuteron and the target, and little r being the relative motion between the neutron and the proton inside the deuteron. So unfortunately I have to switch off this light because otherwise you really can't see anything. So I wrote down what my full wave function, if I consider these two partitions, so in the final state then I have a bound state, that's the neutron transferred onto the target A. So I end up with an A+1 system that I'll call B for the sake of the discussion, the particular discussion we'll have on dp reactions. And then you'll have a relative motion between this bound state and the scattering of the proton that then flies off. So I should, if I construct a full wave function, I should have both components, the deuteron, so phi chi where I'm considering the deuteron channel, and a phi chi where I'm considering the proton channel, where it's the proton that's flying out. So in this particular picture, the phi and P and the phi and A represent bound states that are eigenstates of the internal Hamiltonian of the respective projectiles. So I'll have an interaction between the NP system that then dictates how this behaves. I'll have some effective interaction between that neutron and the target A that then dictates how this behaves. And the energies would correspond to their eigenenergies. In this particular picture, I'm considering just ground states. Okay, so it's the lowest. So now if we take this sort of ansatz of our wave function and plug it in the Schrödinger equation, we can do what you did and worked out with Antonio to reach the coupled channel equations. So we can walk through the various steps in order to get there. So that's what I did. I just said, okay, I know what the Hamiltonian is. The Hamiltonian contains the kinetic energy terms associated with the two Jacobi coordinates, and then contains the pairwise interactions between these bodies. So I've replaced in front of the first term of that wave function, I've replaced the Hamiltonian written in the coordinates that are suitable for that part. So I said, okay, I'm going to use these coordinates to apply on that. So I'll write the kinetic energy term in terms of R1 and big R1. And then I'll sum the three pairwise interactions minus the corresponding energy. I do the same with the second term, but now I use the coordinates R2. In principle, if they Jacobi, they should be well behaved. This should be the same. The kinetic energy term should be the same. So this allows me now, first of all, to identify certain terms that have that are eigenstates of the phi and P. So it allows me to pull out the deuteron state here. So if I put those two together, applied on phi and P, I just get epsilon d. In the second term, if I put those two together, then I just get epsilon b in the way I've defined them, right? And so I end up with this equation where I've just replaced the properties of these wave functions because they are eigenstates of the internal Hamiltonian of their respective projectile-like or target-like systems. Now we're still not there, right? Now typically what we do is we want an equation that is in the relative motion of the projectile and the target. So we're still carrying around the dependence on little r, and so we should really project those out. So let's, for example, project by multiplying by phi and p star and integrating over that. Let's see what we obtain. So this only depends on little r1. Little r1 does not affect the kinetic energy tr1. It does end up affecting those interactions there, right? So those interactions depend on little r1, and so you'd have to calculate the overlap between, you'd have to calculate the matrix element between this term, the sum of those interactions, and phi and p again. So that's phi 1, 1, that's what it is. It's basically the a term that looks very much like what you'd get in the single particle excitation in those equations that you derived, for example, for CDCC. You then get something, well, the energy is still there, and now the tricky part. Now you're going to multiply on the left phi and p on this kinetic energy term in R2. And the kinetic energy term in R2 is a second order derivative in R2, and if you look at R2, it's not independent of O1. So you're going to get some norm matrix coming out because you're applying something that's not orthogonal, and we typically will call that a non-orthogonality matrix that will allow me to transform from one basis to another basis. And then you can't get rid of that kinetic energy term, and so on. So that term looks a little bit like that term. It's now involving a different coordinate system. So if I rewrite this equation, stripping a little bit with simplicities and just put 1s and 2s to make it simple, you can see very simply the structure. You get a term that looks like your standard, in this case, plane wave form. If you put that in there, that would look like the optical model. So if you put something like that into there, you know how to solve that. It would look like the optical model. Then you add another term that connects, that couples to another channel, but now this other channel is in a different coordinate. And in addition, you've got something that will depend on kinetic energy terms in another coordinate with a norm matrix. So this equation is different from that equation in the sense that it's non-local. To calculate the wave function at any R1, you need to know what's going on with R2. So there's something different about this that doesn't really allow you to use the same methodology that you've been using to solve those equations. It is not easily transportable to these equations. So for example, the code you're using can actually solve this through iteration. So it does solve differential equations like this through iteration. But direct integration is, I don't think you can do that. So we should think perhaps of using the other methods. So if you remember, when I think it was exactly a week ago, that I talked about differential equations being transformed into integral equations, and the fact that when you did that, you recovered a certain structure that was prone to certain approximations, that it suggested perhaps you could do certain approximations. And in the process, we wrote down a T matrix that was an exact T matrix, and then we did specific approximations on that T matrix that then allowed us to calculate things that perhaps otherwise we would have not been able to calculate. So we'll go through that, thinking now about this application in particular. And I should point out that even though I reviewed it yesterday, I didn't detect that there were interchanges of coordinates. So I want to make this clear, and keep, unfortunately some of you will still get confused, but I hope that by making the announcement, it'll be less confusing. So I used in this example that I just described R1, R, and R2, R2 to describe the incoming coordinates and outgoing coordinates. Yeah? Very often I also use R and R prime. Other people in other places also use RIs and RFs. So keep in mind that we're going to be using these interchangeably. I don't remember anymore which ones Jeff was using, but I know I was trying to match with those, and then at some point I still had previous ones mixed in. So keep in mind, we'll be talking about, when we go for the deuteron case, the specific case that we want to look at in detail, we'll come back to it in a minute, we'll be talking about R1s and R2s. In more general cases, often I'll be talking about R's and R primes, or RIs and RFs. And you will see these interchangeably in any of the publications that you might be interested in. Okay, So here, we still are 1s and R2s. And you know, you can bunch up the Hamiltonian, taking into account the internal part of the projectile, the internal part of the target. So you bunch up this interaction in there, and you bunch up this interaction in there, and then you have something left over, and you call that a nu. You can write it in this way, and then what you show generally, not for the two-channel case, but generally, is that your equations become something that is very identifiable as what you've been working with before, but then some dependence on a different coordinate system and some non-orthogonality term that creeps in and that you have to deal with. So in the general case, your equations do look like this, where we worked out specifically the two-channel case. So in the general case, where you don't have just a neutron and proton, but you have some core and some, in this case, a neutron that's being transferred, you always can define the eigenstates of the projectile-like system that is bound and the target-like system that is bound. You'll always have a bound state associated with the initial channel and a bound state associated with a final channel. And your Q value for the reaction will be the difference between those binding energies. All else, you know, not taking into account differences in mass. Now, let's think of, in particular, writing this in the coordinate systems of the incoming channel. So if we call it r, little r and big R, then you'd write the kinetic energy like that. You'd have the three pairwise interactions, and you'd naturally want to get these two together because you know the eigenstates, how they're defined. And so let's call that HP. And then what you're left with are those two interactions, and those two interactions are not really in big R. So let's add another interaction that's in big R. So I'm going to add an interaction that is in big R that can somehow be solved together with the kinetic energy associated with big R. But then I'm left over with something that I call nu, and that's going to contain the pairwise interactions that were left over before, minus the ui that I've added. Any questions up to here? So what I've done is write a part that I know how to solve. This part I would know how to solve. The same techniques that I used before would be applicable. I could split the dependence in big R and little r, and therefore it would have what should be by now a pretty straightforward solution. But then I have some other term. I can do exactly the same if I write this in the final coordinates, in this transparency r prime, r prime. So if I do that, then I'd have some other interaction that's written as a function of r prime that I would choose to add to my system, so that I can then split this part of the Hamiltonian into something that depends on r prime, big R prime and little r prime. And then I'd have some leftover, and that leftover would be defined by the leftover of the two pairwise interactions minus that final. Is it clear up to now what I'm doing? I'm just adding and subtracting, and then bunching terms and identifying that certain parts I know how to do. So I want to do a transfer of this nucleon from the projectile to the target. Does the interaction ui of r do that? So what does ui of r do? We've been dealing with things like ui of r since Wednesday, last week. What does it do? What does this interaction do? Does it do anything? We might as well drop it then if it doesn't. What does it do? I've got a projectile, it's got a target, I've got interaction that depends on the magnitude of big R. What does it do? Can it excite the projectile? Corinne, what can it do? So what would you produce from it? Madalena, what can you produce from it? I'm going to start asking specific to people. No, Jeff, you're not. It's on the center of mass of the projectile. So it will affect its motion. It will produce elastic scattering. Optical model, right? I mean, this part is the optical model, is the part that we've been dealing for a long time. So if you have an interaction that depends on the center of mass of the projectile and the target, and there's no dependence on internal coordinates of either the projectile or the target, you will not be able to excite those degrees of freedom. You haven't included them, so you can't excite them. So this part, if you look at this part, if you didn't have that, you would split your Hamiltonian in these ways. That part will contain some motion of the relative motion of the projectile, but if it's in the ground state, it's in the ground state. That interaction is not going to interfere with that. So if you look at the second equation, something similar happens in the exit channel, right? You have written it in such a way that this term here in the exit channel will not be responsible for any transition, cannot be responsible for any transition. It would produce the elastic scattering of that outgoing bound state and whatever core you've decided to use. So by choosing this in this manner, I've sort of made it explicit that what's responsible for the transition has to be what's left over. Is it making sense? Okay. This is important realization because it's going to simplify, it's going to make us go in a certain direction. Okay, so let's go back to our optical model. Our optical model contained just the equation that you solved probably many times now, contained just a kinetic energy term plus a potential that depended on the distance between the center of mass of the projectile and the target. And you obtained from this elastic scattering. There's nothing else that can be produced if you're not including internal degrees of freedom of either the projectile or the target. So this interaction is not responsible for your excitation. What did you do when you wanted to include target excitation? You deformed this interaction. You made it dependent on internal degrees of the target. You included a deformation, included angles in the definition of this. It wasn't a spherical interaction dependent only on the distance between the center of masses. You also, at some point, when you did CDCC, you included the distance between the projectile internal, you included explicitly a degree of freedom of the projectile. And so this became dependent on some other variable. And then you could produce something that's not elastic scattering. But that term alone, go back to Wednesday, only elastic scattering. So I'm insisting on this because this is the basis for everything we do afterwards. So if we don't understand this point, then we won't understand why there's certain choices of that UI. What I did from here to here was just sum and subtract UI. That's all I did. So nothing really fundamental. But the choice of the UI was somewhat induced, I'm telling you, was somewhat induced by the fact that I was trying to separate what I know how to calculate and what I don't know how to calculate. Okay? Now we've got, this part of course is when it projects onto the components, it will give me the eigenenergy. So it's simple to deal with. The rest of the interaction, I've got two interactions here really. I've got some leftover interaction plus this ui. I can apply the two potential formula in principle. Now you remember what the two potential formula was about? Two potential formula said that if I have an interaction u1 and an interaction u2 applied in a given system, and I want the full solution of u1 plus u2, the T matrix for the full process was the T matrix for u1 plus the T matrix for the 2 on top of 1. So that term there connected the exact wave function that contains u1 and u2 with the wave function that only contains u1. Still remember this, or it's completely after so many other fresco exercises completely gone? But this is an important result. So I go back and argue this thing does not do anything but elastic scattering. I want to focus on transfer. I want to transfer a part of this projectile onto the target. U1 cannot do it. So how much is T1? For the transfer process, how much is T1? It's not a trick question, it is really easy. Corey, how much is T1? You don't know? Anybody have a clue if the interaction is not responsible for the transition, how much would be the T matrix? 0. Thank you, Camille. Yes.
Do we have real optical potentials 0?
Doesn't matter. Doesn't matter. We're talking about the T matrix, not for the elastic. So this T matrix I'm talking about now in words, that is not actually this one because I'm going to write down how it looks. But the T matrix I'm talking about would be responsible for the transition between the first partition and another partition where a mass has been transferred over to the target. So in that circumstance, it doesn't matter what your U1 is, you can have the absorption you want. It's not going to be responsible for this transition, therefore the T matrix has to be 0. So if T1 is 0, and you can look back at how you define the T matrix. So I derived it only for the single channel case. So you have to go back to Antonio's couple channel formulation to see how that comes about. But if the interaction is just not responsible for the transition, you don't get T matrix. Because it wouldn't connect. The integral would be 0. That is the part that contributes. So this separation that appears a trivial sum and subtract actually boils down the problem to, well, I don't actually have to deal with anything but this term if I write it in T matrix form. So let's write it down now for this particular problem. So for this particular problem, if I choose to work, so remember it depended on whether I choose to work in post form or prior form for the T matrix. If I choose to work in post form, which really means the coordinates that I'm choosing are the coordinates to write down the Hamiltonian, the coordinates are the final state coordinates. So it'll be the R2, R2, or R prime, R prime, or RF, RF. Then I start out with something that's an exact wave function. I have an operator that's responsible for the transition, and the final state is going to be the state that I get when I don't have this new f. In this particular model, the state is when I cut this out, that state is going to be a product of the ground state, well actually in post form, the ground state of the target-like state that's bound at the end, times the relative motion of the core, this C and the rest of the system. Yeah? So that's what I wrote down. I just wrote down, well, exact, then transition, and then the bound state times this relative motion in the exit channel. I can do exactly the same in the prior form. In the prior form, you start out with the exact, it's actually the final state, the exact, and you get this decomposition in the incoming. But it's identical in the way you formulate it. So we worked out that form for whether you choose post or prior, and we saw that you could just interchange those and you'd still get the same result. Any questions here? Am I going too slow? Yes. I get a nod. Yes, I'm going too slow. No? Okay. I mean, if it's not clear, you should really stop me, and I can go back in the material if you don't remember last week's material. So remember also, there's another reminder, DWBA. One of the things that this formulation allowed us to introduce was truncations. If you iterated the Lippenstring equation or the T-matrix equation, you ended up with a series, and you can truncate that series. And to first order, that series looked like this. Well, we've got a problem here that we've split into a part that doesn't produce the transition we're interested in, the transfer transition. So the T1 we already know is going to be 0. And then if we take just first order, what this would entail is the results, chi are the results when we don't include this new bunch of interactions, right? Remember what chi now means for us is the solution when you don't include the news, these operators. So the operator is in the middle, it's not in there. So this means we could actually calculate this because we know what chi is, for our problem we know exactly what they are, and then we could just calculate this matrix element, and that would give us a solution to first order. When would this be good? When would you expect this to be good? So replacing this just by the solution when there is no new interaction really means I cut this out, and now I've got the solution for this part, which is just a product of the state, the bound state coming in, and the relative motion of the projectile on the target. When would that be okay? When would you expect that to work? When u2 is small compared to u1 in that formulation, or when this thing here is small compared to that. Now, for any odd case, that may not be the case, okay? And we will see that in some cases this may not happen, and so doing that approximation may not be okay. But there certainly will be cases, you can think of cases in which this might be small. You can think of cases where perhaps you could minimize some of these terms. So we'll talk a little bit about that, and then Jeff will talk about specific applications to DP and PD. Okay, let's look at this bunch of interactions that I've called, I don't even know what I've called yet. It's the operator responsible for the transition, and now I want to use some nomenclature that's going to stick, hopefully. The first interaction that is included is a binding interaction. Whether you do it in post form or prior form, the first term that I've written is always a binding interaction. It's responsible for one of the bindings, the one that you didn't include in the internal motion. So if we go back again to our, it's the one that's in here or the one that's in there. That one is already included. It's the leftover. There's another binding, and the other binding is the one you've left there. So that first term is a binding potential. The second term is what is typically defined as a core-core interaction. So there's a particle that is transferred to the target. What is left is usually defined as a core. And so the two cores, the core of the initial bound state and the final bound state, that interaction is actually identical in the formulation in post form or prior form. And then there's the interaction that you've chosen, which is an auxiliary interaction that you've introduced in your problem. Results should actually be independent of this. You know, whatever choice should give the same results. In practice, that doesn't turn out to be the case sometimes because you've got truncations of your model space. The difference between these two is usually referred as the remnant term. And we'll think about specific cases where this might actually be negligible. And so you might just drop it. Now in DWBA, as I pointed out, you replace the exact wave function by the product of the internal degrees of freedom, the product of the internal wave function of the bound state times the relative motion. And so if you replace here that product or replace there that product, you're going to get an expression that looks like this. You know, it's a product of bound state times relative scattering state, bound state times relative scattering states in initial and final states. So in the DWBA form, you have identical post and prior, initial and final, but that nu will be written either like that or like that. Okay, now I want to make this point that this UI or this UF is an auxiliary potential, and you could in principle choose it to be anything, in principle. Yes?
I don't understand for the final state, VP refer to binding potential
Of the within the projectile. Within the projectile. And VT is then in the state within the target. So the standard choice, and the choice that we've been using in nuclear physics, that we've been using since the 60s, more often I would say, is DWBA. And the choice in DWBA is that this potential that you choose actually reproduces elastic scattering of the corresponding system. So if you choose, for example, if you are dealing with DP and you choose this interaction, you choose deuteron elastic scattering, you fit deuteron elastic scattering, and then that UI is defined in that way. The choice in CDCC, if you were going to do CDCC coupled to transfer, then the choice in CDCC might be a folding of the sum of the fragments within the projectile and the target, folded over your states, bin states or bound states. And you could choose to also define this interaction such that it would exactly cancel that term. All these formulations give their own theories. So you'd get different models for each of these formulations. For the sake of what we're defining, we might stick with this for a while, and then Jeff will introduce some specific formulations that rely on this term being small so you can neglect it. So this term, as I said, in principle is important, but there are certain reactions where you might write it in such a way that it's not. So let's work it out specifically for the DP. So what is that nu I for a DP reaction? Nu I contains the binding potential. So I'm writing it in prior form. So nu I would contain the binding potential here. It would contain the core, so in this case it would be the proton and the target, minus some interaction that I've chosen in the initial channel. Let's say it's a deuteron target interaction. In the post form, this would actually be the binding potential for the neutron and the proton, plus the core interaction, minus the potential that you'd get for the proton and the composite B. Let's call it UPB. So if you look at this, and you take the target to be, I don't know, lead-208. Proton plus lead-208 and proton plus lead-209 look exactly the same. Right? That you don't expect this effective interaction to change very much when you add a neutron. So this term actually you can expect to be negligible, and then you end up just with V and P. And then you'd write a T matrix that contains only that term. That makes life a little easier perhaps, because now you're only sensitive to things in the range of the NP interaction. So if I write down the T matrix for that process, I would have a 3-body wave function in the initial channel, effect of this interaction going onto the final channel, and in DWBA what you do is you replace that full 3-body by a deuteron wave function times the relative motion of the deuteron on the target, and you end up with a shape like that, like we just saw. If you do the prior form, you can get to a similar form, and you verify that you should have equivalence in the initial and final. The initial and final look the same, that transition slightly different. Okay, I think that you can work out, so this what I did here is work it out for PD instead of DP. So you can now work out what I just worked out for DP, you can do it for PD, and hopefully conclude that you get the conjugate in terms of the T matrix. Okay? So hopefully the exercise will help you also understand how these effective transition potentials are defined and how your T matrices go with them. But the message is, from the formulation in terms of differential cross-sections, you get to an equation that is more complicated to solve than the standard direct integration methods would allow you to do. And so our field has gone very much into the T matrix realm and defined things in a way where you can either use directly iterative procedures or do expansions and do truncations that are insightful, I mean, in terms of what the physics of the problem that you need to contain is. Questions? Yes.
Can you show the slide before?
Which one?
No, that one. How do you choose the potential between N and A?
Okay, so
N,
the
A, because on your left diagram it's an optical potential,
okay.
and the right diagram it's a bond state potential.
So I'll repeat the question that Pierre just posed in our language. So the neutron A interaction, if we were, let's say, going to do CDCC like you did yesterday. So you did this exercise for the deuteron on nickel. So A is nickel, then you got the deuteron, there's a neutron-nickel interaction. What sort of interaction did you choose? Where did you get your interaction? Come on. Barbara, you were getting your interactions. What did you do to your interactions? What did you choose for that interaction? Nobody remembers? Yes? You chose an optical model. So you said it's 40, there's 18 MeV, I want to split the energy, and so I've got 40 MeV for this neutron, and I'll just do optical model on the target. Okay, and I know you did that. I remember you doing that. Okay, what about what you would do here? You want to have a bound state, and the bound state has that neutron in some orbital, I don't know, 2s1/2. No, for the nickel probably not. I don't know what it would be for the nickel, but you'd have an orbital. You didn't do it, it wasn't part of the exercise, but that's the question. The question is it going to have an imaginary term? If you want a bound state, is it going to have an imaginary term? What did Jeff tell you about binding potentials in imaginary terms? Binding potentials are real. So, you know, if you have an imaginary term, your amplitude decays, right? You lose your amplitude. It decays into something else. So you don't really want to have an imaginary term. You want a binding potential. You want it real. So in the formulation for transfer, we are bound to a choice in these interactions that are real potentials. But it does pose a question that is, well, perhaps you then end up with an inconsistent picture. Perhaps in some parts you approximating your wave function taking into account one interaction, and another part you take another interaction. Yeah? So fortunately, the case we're going to focus on, dp post-form, is the interaction at the energies we're interested is real. So to reproduce the phase shifts, to reproduce the scattering, you do not need an imaginary term. And so this issue will not transport to the examples we're going to focus on. But in more general examples, where you might have a halo nucleus impinging on a heavy target, then you definitely would have, in principle, an imaginary term in the scattering in the initial state, and then you wouldn't have that imaginary term. So there'd be an energy dependence in your interaction. And remember when we discussed optical potentials and the derivation of optical potentials, in principle, these optical potentials have this energy dependence, have perhaps, microscopically, there's this non-locality that we've thrown out, that we haven't included. So that's a consequence of those simplifications. Any other question? Okay, well, but you have to speak up because I can't hear you. Yeah, I know. It's so it depends what you're talking about, and that's why it's useful that you work it out for the PD. I put it in here. You can then double check with what you've obtained, but you need to work it out at least once to understand how to define these interactions. Okay, I think enough. And now it's in the PDDP world. Jeff. How do we do this? Do we switch it off? Okay. Have you copied it here? Have you copied it here?
Yeah, okay. It's on a roll, it doesn't want to stop.
Yes, we have a problem. I don't know why it's not
The software doesn't want to stop. It's going downhill, it's on its skis, and it's going places, and it's not going to stop for anyone. Shall we continue?
okay.
Okay.
I
So,
but the battery is low.
do you want to change it?
Is it okay, or you want to
Well,
continue?
it'd be better to change it if it's probably going to run out. Okay, the pointer also needs more caffeine. Yeah.
Is it okay?
Okay, thank you. F5. Okay, good morning, everybody. So I'll I'll make a start and then we'll have some coffee, okay? Because I think you can only do so many transparencies before you need some coffee. So thanks for Philomena to taking on that challenging interaction, because coming at transfer reactions in the general case, as you saw, there's different ways of writing the transition matrix element. You can do a post or a prior, and so it looks very, very general. And as she said, you really have to sit down with a blank sheet of paper or two and work through it carefully to understand in any particular reaction, DP, PD, PT, D-helium-3, what is the initial state, what's the final state, what all these U's and V's mean. Okay, so it is daunting and it's difficult to see. And so to be very much more specific, and because of what I did the other day on iconal and knockout, if you remember, part of the emphasis and wish to do knockout reactions, we had an exotic projectile. We used oxygen 23 as an example when we talked on, when was it, Tuesday? It's just one big blur. But on Tuesday when we talked, we were talking about a reaction where you were able to pull a neutron out of an exotic projectile and learn something about the quantum numbers of the orbital that had been occupied by that nucleon. And in that case, the observables were what the momentum distribution looked like, how narrow it was, and whatever. Okay, so we had a route to spectroscopy, understanding about the orbitals of particles that were involved in the reaction by looking at certain observables with those fast collisions and nucleon removal. Okay, so to make contact with that and just try to make clear that you can try and learn the same information using a transfer reaction, I'm going to particularly stick to PD. Okay, so a proton comes in, it's going to pull a neutron out of the nucleus, and that's sort of basically the same mechanism and trying to look at the same nuclear structure if you do the other reaction with a fast beam. Okay, so I'm going to take very much more a practical application. We're going to throw away these remnant terms, which if you've got time and if you're really interested in transfer reactions, you have the opportunity with the stuff we'll be doing this afternoon to go and check how important those are and whether it's valid to throw away those remnant terms. But to keep the discussion going so that we can see a path through to what it is essentially that a transfer reaction is telling us, I'm going to keep to a rather simple matrix element. Well, it's a realistic matrix element, which is the one that's normally calculated for a PD reaction, for instance. Okay, so as I say, nuclear spectroscopy via nucleon transfer, but I'll be talking about neutrons, okay, to match up, as I said, with what I did the other day. Okay, so here's my plan. I want to discuss in some detail the different sort of physical inputs you need. And they say they've all been hinted at by Philomena. We're going to have distorted waves, we're going to have complex potentials in various places that describe things that are coming into the reaction, such as protons, and then there's deuterons going out. So I need to describe those motions. Again, going back to what I said in the very first day, most of reaction theory is that we've got pairs of bodies. So in a PD, there's a proton incident on a target, and I need a two-body interaction to describe that, and it's a high energy collision, so it's complex. So you have an optical potential describing protons incident on the target, and then there's an NP interaction, which is a real interaction, which is binding the neutron and proton to form a deuteron somewhere in the problem. And once the deuteron has been formed, it then goes away, and so it's scattering from a residual nucleus. That's a high energy, so that will be described by an optical potential as well. Okay, and the neutron was originally bound in the nucleus. Remember, that's to do with overlaps, okay? And I'll come back and remind you, we discussed overlaps. And so there must be an interaction also somewhere which is binding the neutron to the original nucleus which it's being removed from. So the whole problem is really about different two-body systems. Two bound states, a neutron bound in the original target nucleus, and two scatterings which tell me about the scattering of the incident and the final particles. Okay, so I want to talk about these various inputs we need then to do a realistic transfer reaction calculation. I say I don't want you to forget that when we talk about bound states of a neutron, being removed from a real nucleus. Well, actually what we're talking about is overlap functions and spectroscopic factors. Okay, and those are important for determining the reaction yields. And we've discussed independent particle model estimates for what spectroscopic factors are. Okay, and we did that quite carefully previously for taking a particle out of the nucleus. Now we also want to do dp, where we put a particle into the nucleus. Okay, so there's a more formal assignment, you know, equations and whatever this afternoon. If you want to think about the relationship of spectroscopic factors when you take a particle out versus the spectroscopic factor when you're putting a particle in, there's a little bit of algebra, and those are related to each other, but they're not equal. Okay, so there's a little exercise there, and so that's an important aspect because it's a confusing issue, and if you are involved in DP, PD, this is a good opportunity at this school to clarify your thoughts about how that works. Most of the discussions I find in the books are rather confusing on this point. Okay, and the other thing I want to try and make clear, the essential physics that you probe in a transfer reaction. I'll do that by throwing away distorted waves at some point and just doing it in plane waves, and then we end up with Fourier transforms, and so Fourier transforms tell us about the momentum content of different wave functions. And so if we do the matrix element in plane waves, we get an idea of why the angular distribution of deuterons coming out or something is oscillatory and why it's got the magnitude it has. Okay, so that's my plan, and we can't possibly do all that before coffee. We may do some bit of this. Okay, all right, so this is going back. Now we're very specific. If we're talking about PD, then we can get into the coordinate systems in more detail. Okay, and this also gives you an opportunity to feel good, because you can revise your first year undergraduate vectors addition and draw some vector diagrams like this and begin to understand what's going on. Okay, so we're talking about PD, all right? So that means I've got a proton incident with some laboratory energy and some instant momentum direction on a nucleus with A+1 particles, and after the reaction we put a detector somewhere and we measure deuterons coming out at some angle with some momentum. We conserve energy, so there's obviously simple kinematical relationships between these things. Okay, and there's all these vectors. Okay, so why do we need all these vectors? Well, there is a neutron which is originally bound to this guy, so we're going to need this coordinate here because it describes the motion of the neutron moving with respect to the original core of nucleons in the original nucleus. Okay, this is the relative motion coordinate, and we need that because there's an interaction between the neutron and the proton, and we have a bound state of the deuteron, so that's going to involve that internal coordinate little r. Okay, right, so then we obviously going to have, this is a sort of three-body problem, so we've got a potential acting between the neutron and this, so this coordinate here in which the bound state is also, there's going to be a neutron target interaction in this coordinate, and there's also going to be an interaction in this coordinate, okay, VPA, okay, whereas this coordinate here between the proton, which is incident, and the center of mass of the original nucleus describes the original coordinate for the relative motion of the proton and the A+1 body system. Okay, so I hope you can see that all these vectors here are going to have some need to them, and the last one here is the vector from the core of the A nucleons and the center of mass of the deuteron, the neutron and proton. So that's the vector for the outgoing particle after the reaction. Okay, so asymptotically, this coordinate gets big in the incident channel because these two are bound, and asymptotically in the deuteron channel, big R is getting big, and these two form a bound object. Okay, so the idea of this slide is just to make clear what all the vectors are, very explicitly in this case of PD. Okay, and we can draw the vector diagram, and all those vectors are going to appear somewhere through the slides. Hope you can remember what most of them are. Okay, so let's go to this matrix element that we've been talking about. So this is what having thrown away a small remnant bit. Okay, I'm not going to talk any more about the remnant bit. This is what we would normally think of as an exact matrix element for a model of the PD transfer reaction. Okay, and it's not distorted wave Born approximation yet. What we've got here is an instant proton on an A+1 nucleus. So this describes the entrance channel. There's the NP interaction, which is the interaction primarily responsible for the transfer taking place. Okay. Now in a PD, I think it's fairly obvious that this interaction, the NP interaction, must be the dominant interaction in making this reaction go, because I've got a proton coming in and I've got to end up with a deuteron going out. Okay. So the only way you can do that is if a proton comes in, gets close enough to a neutron somewhere, the NP interaction acts strongly, binds those two together, and they go out together. Okay, so without the NP interaction, this thing doesn't go when you write this form of the matrix element. Okay, and so there can be some other little bits in a remnant, but we're not going to discuss those any further. Okay, now in the outgoing channel, I say this is called exact because in the outgoing channel, I've got a residual nucleus in some final state here. Okay, and then I've got this wave function here, which is not a distorted wave. It's not just an elastic scattering wave of a deuteron from the target nucleus. It's actually a solution of this three-body problem where a neutron and a proton are incident as a deuteron on the nucleus. So think of this time reversed. Okay, that's a psi minus. So this is a sort of time reverse state. Okay, so you've got to think about this thing as a time reversed version of the positive going state, and this describes a situation where a deuteron comes in to a nucleus, the neutron and the proton are interacting with the nucleus via these interactions, and it can either stay bound as the ground state of the deuteron or it can break up. Okay, so it's exact in the sense that this still includes full three-body degrees of freedom of the deuteron and the target nucleus. Okay, so this includes processes, for instance, where the deuteron or the neutron, okay, the proton comes in, it finds a neutron, okay, and it might find the neutron and go immediately into the ground state, or it may find the neutron in some configuration that the neutron and proton find themselves in some excited state, some broken up configuration, and then they interact and they couple to form the deuteron later on. Okay, so this includes effects where the neutron and proton also appear in the continuum as well as in the deuteron ground state. We'll come back to that again later. Okay, so this is the form of the exact matrix element, and in a moment we'll go to distorted wave Born approximation, where we say let's make the assumption that in fact in the final state the deuteron is always in its ground state. There's no excitation effects put in which case what's over there will become a distorted wave describing elastic scattering of the deuteron only. Okay, so the other thing I want to point out, reminding you of where we've come from in these last couple of weeks, is that there's an A+1 body wave function, an A body wave function there, and so this motion of this particle which is being collected is actually appearing. What we do, if you remember from our previous discussion, is that there's an A+1 body wave function on this side, there's an operator, there's an A body wave function on that side, and somewhere in this matrix element there's going to be an overlap, a matrix element involving these guys, okay? And this is going to turn into our what we call the bound state wave function of the neutron. What it really is the overlap of the initial A+1 body wave function with the A body final state. And this is a one coordinate variable in terms of the remaining particle, which is no longer in this system. Okay, so I'll write down the equations again and remind you what's going on there. Okay, so first of all, let's just write the distorted wave version. It looks exactly the same, pretty much, except, as you say, we've taken this wave function here, which allowed the deuteron to get excited in the final state, and replaced it by an elastic scattering wave where the deuteron is now firmly embedded in the ground state, and so the assumption in this matrix element is the proton finds a neutron, populates the ground state instantly, and the deuteron goes out in the ground state, having happened as a one-step transfer in that way. Okay, so in the exit channel now, this wave function is a solution, as Philomena has told us. It's a solution of a problem where there's only one variable. It's a center of mass variable. This is the kinetic energy operator. The only thing that can happen in this wave function is elastic scattering. Okay, there is no dependence in this equation on the little r variable, which is the internal coordinate, and so this equation, just by looking at it, is a function only of r. It only affects the center of mass motion of the deuteron and describes elastic scattering from the residual nucleus with A nucleons in it. Okay, so this is what we're going to start by thinking about, and this is, you can calculate this afternoon. We will calculate this afternoon, and we have the ability to check what is the sensitivity to what all the things that are required to compute this transition matrix element and the resulting cross-section that comes from it. Okay, so again, I think all the things we have to consider in DWBA are really on this slide. Okay, you'll now see that the neutron-proton interaction is still the dominant interaction, and it now comes along for the ride with the deuteron wave function, the deuteron bound state. Okay, so all the information about the internal coordinate, the relative motion between the neutron and proton, now appears in two places, in there and in there. And so very often this product, which is called a vertex function, it's the way the basic NP system enters the reaction, sits in there. And they say VNP and phi d describe the internal motion of the deuteron effectively. Okay, and say this is the name it's often referred to, and you will know from everything you've been told about nuclear physics that the neutron-proton interactions are rather short range. Okay, the longest piece is 1 pion exchange. There's stronger pieces at small distances, and I don't know what mentally picture you carry around in your head for how extended the neutron-proton interaction is, but by the time you get to 1 Fermi, it's getting weaker, and in around 0.7 Fermis or something is the strongest part of the nucleon force, whatever. Okay, so this is quite a short range object. Okay, and so there are approximations you can make to say, what's the shortest range thing you know? You could have a Gaussian. Okay, you could have a Gaussian, attractive, with some short range. But I say if we take the limit, the shortest range thing we would not normally write down mathematically would be a delta function. Okay, delta function as a vanishing range. Okay, it's very big, but at one point. So one way you can approach a solution of this T matrix in a very simple way is to say, I know this is a short range object. What do we get in the limit? That in fact that product is a delta function in little r, which says that the interaction only happens when the neutron and proton are actually physically in contact with each other, rather than being 0.7 Fermis apart or being 1 Fermi apart. Okay, so we'll discuss the way the finite range of this object enters into this matrix element. Okay, now I think the first thing I'm going to do after showing you this slide is just remind you of this bit again. Okay, I'm sorry if I keep reminding you of this overlap, but it's crucial if you're doing nuclear structure considerations using reactions to understand the connection between the reaction and the many-body wave functions of the nucleus. Okay, whether you're a shell model person and you calculate these things using the shell model, as Ed showed you how to do last week, or whether you're a microscopic person and you try and calculate a 23-body wave function for sodium-23, I guess, if it's 23 bodies. You know, no matter how you get those wave functions, what you put into the transfer reaction is something that's extracted from many-body wave functions. Okay, and we can approximate that by having a Wood-Saxon well and dumping the particle in the well with the right separation energy, and we can make an approximation to this overlap. Okay, so let me just remind you. Okay, overlaps. Remember, the assumption is that the process perturbs, changes the motion of just a single nucleon. Okay, we have called that, we're going to think of it as a neutron again because we're talking about PD, and we call that particle particle 1. And in this case, the operator which is responsible for ripping this neutron out of the nucleus, the operator that affects only coordinates of particle 1, the neutron, is the neutron-proton interaction. And that involves the interaction of the incoming proton that's coming in with this neutron in the nucleus, which I called nucleon 1, and so it only acts on particle 1 coordinate. Okay, it acts on the coordinates of one neutron, the one that it's going to bind to, and that's that. Okay, so this operator here, which is singling out the coordinates of this nucleon for special attention, has been changing as we've gone through different reactions. Okay, in the knockout, it was 1 minus the modulus of the S matrix of the neutron squared, which told us about the absorption of that nucleon. Here, it's the neutron-proton interaction, the proton coming in and seeking out a neutron, and our neutron is called number 1. Okay, so again, our PD matrix element looks like the T matrix that I've always written before in this generic form. I've got an initial nucleus. My old notation was Y. I'm going to end up with a nucleus X containing 1 less nucleon. There's an operator that operates on 1 particle coordinate only. And so when I calculate a cross-section from this, I've considered only one of the neutrons. There are n identical neutrons in this nucleus, and so the cross-section will be n, the number of identical particles, times what I calculate by calling a nucleon nucleon 1. Okay, there's n equivalent situations where each of the other nucleons I call nucleon number 1. So there's a factor of n times this T matrix. Okay, and again, the important thing is that because the operator sitting in the middle depends only on particle 1, I can pass it through this matrix element, and what comes in then is the overlap integral between the A plus 1 body system and the A body system, and we've discussed that at some length. Okay, so another thing that's important for the transfer reactions is to remind you that of what we did last Tuesday. Okay, this overlap function, as we've seen, contains some angular momentum because we've got spin A and spin B, so we're going to need a Clebsch-Gordon coefficient somewhere. But we were able to show last time that this function, this overlap function, satisfies a differential equation, an inhomogeneous differential equation, and that inhomogeneous differential equation has as the energy, the relevant energy, the separation energy of the neutron from the nucleus. Okay, and what we saw when we did this before is that if you ask what does this overlap function looks like at large distances, well, at large distances this source term goes to 0, and so we are guaranteed that our overlap looks like, in the asymptotic region, it looks exactly like the asymptotic form you get for a single particle state bound in a potential well. It's got a Hankel function form, and goes as a decaying exponential. Okay, so our bound state gets the asymptotic form of the wave function correctly. What is missing is what is the constant that multiplies this. Okay, and the constant that multiplies this, if I have a normalized single particle state or I calculate the form factor microscopically, will be different. Okay, so it's the magnitude of this tail which is important. You get its functional form for free. It decays away, but you need to find out the number that you need to multiply by. And this is very important in transfer reactions, okay? Because transfer reactions are used very often to try and extract this coefficient, the magnitude of this tail, because when we talked about this before, as I said, when you're doing certain sorts of astrophysical calculations, where the energies are low and the nuclei come together and they stay at reasonably large distances, it's just the tail of the wave function that you see. And so you need this tail, the magnitude of the tail. Do you remember what it's called? ANC. What's it called? Asymptotic normalization constant. Okay? So there's lots of papers out there in nuclear astrophysics and others where people are trying very hard to measure the ANC, the magnitude, the constant that sits in front of that Hankel function tail, or if it's a Coulomb, it would be a slightly more general function if the particles are charged. But measuring that constant allows you to know exactly what the wave function is doing at large distances, and then you can put that into capture reactions or other calculations which are relevant for astrophysics. Okay, so just the note at the bottom there that the norm, the magnitude of the tail is very important. And you get that tail right even by using a simple potential model to describe the form factor as the way we've been doing during this course. If you can calculate this form factor exactly from a microscopic theory, that would be even better, but that is a tough job to do. But you can see from this expression how you might do that if you had a microscopic wave function. Then you can construct this source term on the right-hand side of the equation and solve an inhomogeneous equation to find f, which is the thing that goes into the transfer reaction. Okay, so the remaining thing, say, just to remind you of this slide, so that to just remind you where all these factors of n due to n identical particles disappear to, because they don't appear in the final expressions that we calculate the cross sections for. Okay, so let me remind you, there's the overlap, Clebsch-Gordon for the angular momentum conservation, as I told you before. Okay, and the way we relate the magnitude, say this function which comes out of the realistic form factor and our normalized single particle state is we define something called a spectroscopic factor, and if you remember, this thing which is in the real form factor is defined as the square root of the spectroscopic amplitude or the square root of the spectroscopic factor over the square root of the number of neutrons. Okay, and so just to remind you that there is a factor n here, square rooted, and when you put that into the amplitude, it cancels the other n that was upstairs due to the n identical particles in the cross section, and so at the end of the day there was an n upstairs and an n downstairs, and then it just disappears off the scene and you never consider it again. Okay, and so let me just jump to this slide then. So the way when you put all those things together, here is our so-called exact three-body amplitude. Okay, this is the one without the distorted wave in here. So all I'm telling you is that this guy and this guy collapse because of the overlap argument here, and they end up with the square root of the spectroscopic factor times a normalized single particle state, which we would normally calculate in a potential well. Okay, and if you put those things together, I say I'm not going to carry the n which was upstairs because there was a square root of n under this guy, and the amplitude then looks like this. Okay, so we've got rid of the many body nature. Okay, what we've got now is the final state wave function of the deuteron. That should also have a little r coordinate in there, beg your pardon, I'll have to fix it. This is the final state wave function. That's the initial bound state wave function of the neutron. This is the proton distorted wave. This is the NP interaction. Okay? And the cross-section doesn't have any factors of n anymore. So the cross-section contains some factors like reduced masses, the usual phase space type factors that appear in cross-sections, factors of h bar squared. Not going to complicate the equation by that. So this is some constants times the spectroscopic factor times the square of this T matrix element, which is calculated with a normalized single particle state. Okay? So this is the exact expression, the exact three-body model expression for PD. Okay? So I'm just trying to remind you, on top of everything that Philomena has told us, there's this reduction that goes on. Okay? So I think we try and be precise in the language. Okay? The bound state wave function here is a representation of the overlap function, the one nucleon overlap function due to these two nuclei. And the spectroscopic factor is coming from this many-body part of the calculation and sits there. So one number contains all the many-body information, really, about the structure of the nuclei involved. And So you get S from your favourite source. Okay? Or you calculate this and you measure it, and then you take the ratio of one to the other, and you can determine S experimentally by fitting your calculated cross-section to the data to try and extract that number there. Okay? And then you can compare it with theory, of course. Okay, so I hope that's the starting point from which we're now going to continue to work, and we can make the distorted wave variant of this by replacing this by a distorted wave, an internal neutron wave function. Okay, and this is the cartoon down below then. Okay, so for practitioners, if you're really interested, you've taken some data, you want to calculate a PD cross section, this is really the normal starting point that you'll find in the books, and this is what the codes do for you. Okay, they either calculate this with some approximate version of this three-body wave function there, or they calculate this thing with a distorted wave times a neutron wave function in that point there. But say everything we've done before that, we can sort of brush to one side. We've done all the spade work now. We've dug a nice clean hole, and this is the hole we're going to leap in. Okay, this one here. Okay, so what I want to do after coffee, because I think it's a good time to stop here, is go back to our example that we did for knockout last time. Okay, so to be specific, last time I said let's think about some separation energies and spectroscopic factors and occupations for a particular case. And last time we looked at oxygen 23, neutron knockout. Now I want to talk about oxygen 23 PD. It's the same nucleus, it's the same nucleons we've got our eyes on to take out. The mechanism for taking them out is now different. We send in a proton looking for neutrons to collect and come out as neutrons. Okay, and so after coffee I think we'll come back to this and let's talk about some sensible choice of parameters that we might use. What would be a strategy for calculating those sort of matrix elements I've just been showing you for such a system? How do we choose the potentials? What do we know experimentally? What's a strategy to take us from that point a little bit further? Okay, so let's take a break, and then we can go through the rest of the slides and discuss that after coffee. Okay. Please. Maybe we should just take it to the coffee room, and then we can. No coffee.